All right, what's up, everybody? I'm Hunter Hayslip,
And I'm James Chapman.
and today we're going to be talking to you about device drivers. So, a couple things we want to touch on in this presentation is loading into an OS, and then also methods of the input and output. So, as you see here, there's three different kinds that we're going to talk about. We're going to talk about busy, interrupt, and then also DMA. So, you might be asking, what are device drivers themselves? So, they're actually a special software that is used to control hardware. Most commonly today, there's a lot of gaming PCs out there, and different people put different kind of parts and connect them to their PC. Well, they're pretty much nothing unless they have device drivers. So it's something I like to refer to it as it's the nervous system of the PC. So without your device drivers, pretty much your CPU, your GPU, your RAM, pretty much everything that you see in this picture over here is going to be worthless. It's going to be nothing. It's just going to sit there, and it's actually not going to power your computer at all. And your computer probably is just going to be the exact same as it was when you bought it. So you can pretty much say that they're essential for the operating system to communicate with the input and the output devices, which are also your hardware.
So, as for loading into an operating system, your device drivers work on the same level, or work on the kernel level of your operating system, which is where all of the systems that like control the general structure of the computer reside. When they are installed, the operating system will load that driver in order to call it on the device itself to make sure that all things are connected and like working together in tandem.
You might be asking, how did they get here? And James is actually going to talk about that for us.
So, as was stated before, the device drivers are essentially the facilitators between the operating system's commands and the device itself. They handle all the input and output calls to and from those devices to make sure that they flow perfectly fine. In the beginning, Unix developers didn't have too many devices that they needed drivers for, really. So they would take what few drivers they had and built them right into the operating systems. And because they didn't need too many, they didn't need constant updates, they would just have to recompile the entire kernel every time to make sure that those drivers would work. But since more devices, your printers and your scanners and whatnot started to come out, and people needed more of those devices, MS-DOS was one of the first ones to change the system so that you could just download drivers and have them work with your operating system instead of having to recompile the entire kernel.
Yeah.
Yeah, go ahead.
And when did this actually happen? It was on the pretty much when personal computers started to roll out. That's when a lot of people were like, "Hey, actually, I want to get involved on this," and they started to kind of install new things on their computer, different network adapters and drivers and things like that. And so that's kind of being said. That's what prompted that development to actually have more drivers because there was more devices with more of a variety of different kind of input and output devices out there. People could afford them. They could actually install them, and they can put them on their PCs. And as of today, where can we see this going? It's going to be more customization. So as gaming is taking off in PCs, and you're seeing a lot less consoles, it's actually going to be a lot more drivers. Just because, like we said in the bullet point above, there's more devices. So whenever people want the new GPU that's coming out or the new CPU, and they want to add these bigger RAM chips actually into their computer, they're going to have to download these device drivers, which are going to attach to it, act as a middleman, and actually communicate with the OS, saying, "Here is what is happening. Here's how our operating system is reacting to the actual physical hardware components," and that's just how it's going to take off. I believe in the future, it's going to be a lot more.
So, strengths and weaknesses of the device drivers themselves. Unfortunately, they are not flawless. Drivers have no ways of telling how many calls they may receive from an operating system. So, if those are not accounted for, then it could cause interruptions that just cause the entire device to stop whatever it's doing and abort all things that it has decided, which is not fun. Um, and unfortunately, because there are so many devices out there made by a number of different manufacturers, there's no way to confirm that their interfaces, how the operating system can interact with them, is always the same. So while the device manufacturers will have to worry about drivers that can mesh with in place operating system developers are going to have to account for drivers that may have extraneous interfaces to deal with.
Yeah, well, that being said, there are some strengths to device drivers, and the number one thing that I could think of is the simplicity. Instead of like what they had to do in the old times, they'd have to reprogram the OS and then recompile the kernel. Instead, now we can just install a single file. It runs an application onto our computer, and then that device driver is dynamically loaded into the system, and it pretty much handles all the interactions. It's super simple, pretty much 1 to 2 click, and it automatically just load into the OS and say, okay, here's what I'm detecting, here's what kind of hardware we got, and let's roll. And so, as we said in the very beginning, there's different methods of input and output, and we're going to talk about the three today. So, with the first being busy, so it's actually the simplest method of input and output, and this typically happens when the user issues a call to the kernel, which will then boot up the appropriate driver that it needs. This driver will sit there and just continuously loop and loop and loop. While it's also looping, it's also polling the device to actually see if it's done. So it's going to the whole time just be sitting there and checking to see if this device is done. When it is done, the driver will then pull that data that is necessary and place it where it needs to, and it will also return. So this will signal to the OS that the to return the control to the caller.
Whereas the interrupt method, instead of just waiting and constantly asking the device if it has finished, the driver will instead do its own thing and say, "All right, device, interrupt me when you finished your task. I'm just going to keep doing whatever I need to do." That way, the operating system uh, can give a lot more control back to the user to start whatever other processes that they may want to, and it will only like bar them from acting when it needs to complete those actions.
And then lastly, we have DMA, which is actually it uses a direct memory access chip, which is where DMA comes from, direct memory access. But this direct memory access chip can control the flow of bits between memory and a controller without constant CPU intervention. So it's super really cool to me that it can actually control these flow of bits and not even have a CPU be sitting there and watching it. So the next bullet point says that the CPU sets up the chip by telling it how many bytes to transfer, what the device and memory addresses involved are, and then the direction that it needs to go. So when the chip is done, this will also cause an interrupt, as James talked about before. All right, this is a little thank you just for watching our presentation. This is the device drivers presentations, and I was Hunter.
That was James.
Thank you. Also, here's our reference slide just for reference. We used typically pretty much just the book, which actually had everything that we needed in there. And then we did use one website because we liked one of the quotes that we pulled out of it and what it said.